Okay, so in this problem, we're absorbing N-butane from a light gas into a heavy oil at 1000 kPa and 15 degrees Celsius. Absorbing means that the N-butane is going from the gas to the liquid, so it's basically going in this direction. And this seems like a fairly typical absorption problem. The only really unusual thing is that the equilibrium data is provided in the form of a de Priester chart. Using a de Priester chart is quite simple. We know our operating conditions, so we simply need to take a line, draw a line that connects the temperature on the right side and the pressure on the left side, and then look at the corresponding line for our substance, which is N-butane. So let's go ahead and do that. So we need to take a line, and 15 degrees Celsius is here, and we need to trace it and connect it with 1000 kPa for here. Now, where is N-butane? N-butane is here, so now we just need to zoom in, take a close look at where this line intersects. It looks like this line is intersecting at a value of 0.22. So the value we obtained from the de Priester chart is the K value. So K is equal to 0.22, and K is simply the ratio of the vapor fraction to the liquid fraction. So that means that we have the relationship y is equal to 0.22x. So now we can simply plot our equilibrium line, which is going to be this linear relationship here. And to do that, let's just write down the series so that we can plot it afterward. And for the y, let's make our lives easy and choose some y value of significance. So we have y equals 0.0004 and y equals 0.003. So to make it a bit easier with the plotting afterward, we'll choose a common divisor. So we'll take y equals 0.0002, and then we'll use that to plot the rest of our series. So let's do that all the way to y equals 0.003, and then x is simply equal to y divided by 0.22. So now we can plot our equilibrium line. Since the mole fractions are much lower than 0.10, then we can assume that this whole system is dilute, so therefore we don't have to worry about the flow rates changing. That means that we can use the same constant flow rate throughout, which is L is 75 kilomoles per hour, and B is equal to 150 kilomoles per hour. And now, since we know the flow rates, and we know most of the entering and exiting compositions, we can actually calculate the operating line. Recall that the operating line equation is L over V times x plus y1 minus L over V times x0. So we can go ahead and trace it. So this is going to be the liquid flow rate here, divided by the vapor flow rate times x. And there we go. In an absorption problem, then the operating line is always going to be above the equilibrium line, and that's what we have. So that means that we've calculated it correctly. And from here, we can just simply find the number of stages from mechanical delay analysis. So once again, you start from the operating line at your concentration of interest, which is going to be here, and then you step down until you reach your exit concentration, which is y equals 0.0004. Okay, now that we've traced our steps, we can see that we need approximately 2 stages to get to y equals 0.0004, and so that is our answer, 2 stages. And the final mole fraction in the outlet liquid is going to be equal to the x value here, and it is going to be approximately 0.0016. So we can go ahead and write that down. So xn is equal to 0.000 or 0.16, and that's it.